And in the last class you have seen electrochemical cell, galvanic cell, that you have seen, in which chemical energy was converted into an electrical energy. And as I explained last time, between the device it consists of two half cells. Here left side cell is consists of the electrode, and it's that will be of metal and a salt solution having concentration 1 molar. To left side we take more reactive metal, and on the right hand side we take less reactive metal. And more reactive metal, that is providing your electrode as the nature of anode, and the less reactive metal as a cathode. And so electrons are flowing from anode to cathode from the external circuit, and this is the salt bridge which is linking the two half cells, and this is packed with agar and agar gel, and in the gel we have either KCl or KNO3 or K2SO4. Strong electrolyte but inert in nature, these are packed into it. So two solutions are in a indirect contact, and so current this is completing the circuit, and so current is flowing from cathode to anode, and through this salt bridge to the internal circuit. So through the external circuit you have seen electrons flow, and through the internal circuit current is flowing. Anode, this side, left side, this is called your oxidation half cell, this side is called reduction half cell. So here oxidation is taking place, here reduction is taking place, you have seen. So the whole this cell, that is your having your redox reaction. So this part we have done last time, and so today I will be explaining to you the electrode potential. So the reaction which we have considered last time, if you remember, that is when zinc solid is turned into zinc ion by releasing two electrons. This was oxidation reaction and is taking place in left side, and in the right hand side copper ion aqueous and taking up two electrons and is turning into copper solid. This is taking place in cathode reduction half cell reaction. And overall reaction, electron cancel, we have zinc solid plus copper ion aqueous will give you zinc ion aqueous and copper solid. This is your cell reaction. So last time I told you that how that is one metal will be oxidized with other metal is reduced, and that we are going to see here. And when this oxidation reduction is taking place, what is happening, that the voltmeter which is connected here through the wire between zinc rod and copper rod, that is showing voltage about 1 volt, and this voltage is because of the potential difference. So today I will be covering that is what is electrode potential. Electrode, you know, is a solid part of the metal which is dipped in a solution. So if you have a beaker containing a metal rod, any metal rod, this is metal rod which is an electrode, and dipped in your electrolyte. This electrolyte, if the metal is M, then electrolyte will be having ions of this metal, whatever the valency Mn plus. So here we have, so when electrode metal is in contact of its solution of a salt, then two phenomena are possible. And here I will be, so electrode you understand is this, and potential. Potential meaning is a ability to convert in future to show some special characteristic. This electrode, when it is left out, this will be neither negative nor positive, may be behaving as both. But what is the nature as anode or cathode? That is not known, or that you cannot decide. It can only be decided when it is dipped in its metal salt solution. So in future, what will be the behavior of this metal rod? That is what your actually potential is. So electrode potential is actually the potential difference. This electrode potential is the potential difference between the electrode, that is metal, and its aqueous solution, which is containing metallic ion. This is one thing. And electrode potential is also the tendency of an electrode to lose electron or to gain electron. To lose or to gain electrons, where losing electrons and gaining electron when the electrode is dipped in its metal ion or its salt solution. So when this is happening, when a metal piece, metal electrode, when it is dipped in a beaker containing, as I told you, this is your metal rod, this is dipped in a solution. So this is metal rod and it is here in metal ion aqueous. So what will be the phenomena? Two phenomena are possible. One is that metal solid will lose electron, say n electrons. You don't know what is the valency, number of electrons will be lost according to the valence electrons, number of electrons present in its outermost shell. So here it will be turned into metallic ion. So here what is there? Oxidation is taking place. Then this phenomena is also possible. Metal ion will gain in aqueous solution, will gain n electrons and will be turned into metal solid, and this is reduction. You have seen this in the last class. So these two conditions are there. Either these two or third one is there, neither this nor this. But that is very rare, but we have to consider only these two. So if this phenomena is taking place, here what will happen? Metal which is here present on this rod in contact of the solution, this reaction will take place on the surface and metal ions will be formed on the surface, and from there they will pass into the solution. So here we have got all metal ions present and metal ions are being added, and electrons which are set free, that will remain accumulated here, where on the surface. So electron, they will be accumulated here and all metal ions will be passed into it. So what will happen here? Because of electron accumulation, what is there? This electrode will be turned negative, and it is said to be oxidation electrode because oxidation is taking place, and also known as anode. So when it is turned to be negative, then if this phenomena is taking place, if that phenomena is taking place, in that case, this metal ions, they will gain electron, and when they will gain electron, then they will turn into metal solid. So some of the metal ions, they will be turning into metal solid will be deposited here. So here electrons will be taken up. So this here electron density will be reduced. From where electrons are coming, as I told you, if this is connected, this is one half cell and there will be another half cell say zinc. So electrons are coming from anode to cathode. So this extra electron which are here, that will be taken up by metal ions, and in metal ions, when they will take electron, they will turn into metal solid. So electrons which are coming on this electrode, that is your cathode, they are taken up, so density of electron is reduced, decreasing, and so they will generate a positive charge. So in that case, the electrode will be turned positive in nature, and that is your reduction electrode. So in oxidation electrode, what is happening? Electrons are getting accumulated on the electrode, and in reduction, your electrons are being consumed, and the concentration of electron is decreasing at the electrode, and therefore they are positive in nature. So both of this phenomena which is taking place, metal solid is turned into metal ion by losing n electrons. The example we have seen, zinc solid is turned into zinc aqueous and 2 electrons. This is one reaction with example. The second reaction, that was that the metal ion in the aqueous solution will gain an electron and will be turned into metal solid. The example we have seen, copper ion aqueous will gain 2 electrons and will be turned into copper solid. So here this is. So why this reaction is common in zinc and why this reaction is common in this? That is here, that will not necessary that always this will be undergoing oxidation. This can also undergo reduction. But when this is connected with this, one more reactive metal is connected with less reactive metal, then more reactive metal will undergo oxidation and the less reactive metal will undergo reduction. Why? Because electron losing tendency of more reactive metal is stronger than electron losing tendency of the metal which is less reactive. In other words, zinc which is more reactive, it can lose electron faster or it can be oxidized faster than your copper metal. If copper metal, if I take more faster, zinc is undergoing oxidation than copper metal. And in opposite, if we say, that is what? That is less reactive metal is more easily reduced than your more reactive metal. More reactive metal is easily oxidized but not easily reduced, and less reactive metal is easily reduced but not easily oxidized. So the reaction, that is the phenomena which is stronger, which is faster in a metal, according to that it is going to behave. So if a metal is more reactive in nature, it will be losing electron, will be undergoing oxidation, so always will be forming the electrode with a negative charge, and that will be your anode. So this is your more reactive metal which is showing and always forming negative electrode, and that negative electrode is called anode. In this case, it is always your less reactive metal and always forming positive electrode, and that is your cathode. These are the points you have to remember. So this is about your electrode potential, and electrode potential depends upon two main factors. The first factor is the nature of electrode. The factors on which electrode potential depends. The first is nature. Nature of electrode. What is the nature of electrode? You have seen more reactive or less reactive, having tendency to lose electron faster or having tendency to gain electrons. So, nature of electrode. And the second is a concentration of ions in the light. If concentration will change, what will happen? That oxidation rate of oxidation, reduction reaction will also change. So these are the two important factors on which electrode potential depends. Another factor is, third factor is also there, that is temperature. So with temperature also electrode potential changes. So three factors we have seen on which electrode potential depends. First is nature of electrode. Second is the concentration of electrolyte, and the third is the temperature of the electrolyte. And now I will teach you the measurement of, here I will tell you representation of electrode potentials. So what this electrode potential I have explained to you is, you have got idea that we have got for two half cell. So electrode potential for one half cell, if it is your oxidation half cell, then its electrode potential will be called oxidation potential. So its electrode potential will be called oxidation potential. And oxidation potential, how do we symbolize? Electrode potential is symbolized by capital E, and when we say oxidation potential, so or electrode oxidation potential, then E, and at the base you will write your oxidation, or you can write like this, E metal into metal ion. These are the methods how we show oxidation potential. And the reaction which is taking place in reduction half cell, that is called reduction potential. And for reduction, it will be RED, reduction, and here it will be metal ion into metal. So this is method of presentation of electrode potential of a single cell. So it is also called single electrode potential. So here that is, you have seen this is, the one thing you remember here student, that is when we have the concentration 1 molar and the temperature 298, I told in the previous class also, 298 Kelvin or 25 degrees Celsius, and if it is a gas, this is for the solution, and if it is the gas, then the pressure is 1 atmosphere if it is gas. If these are the conditions, then it is indicating a standard electrode potential. Standard electrode potential is symbolized by E0. So when E0 is there, it means the concentration is 1 molar and the temperature is 298, and if it is a gas, then pressure is 1 atmosphere. So keeping this thing in mind, now I'll teach you how you can find out electrode potential of a half cell. Now just I draw the diagram quickly for you. This half cell you have seen, that is your salt bridge, and here is the rod, here is the rod, this is zinc sulfate, 1 molar solution, copper sulfate solution, 1 molar, and this is your copper rod, and this is zinc rod, this is anode which is negative, this is cathode which is positive. This is opposite from the electrolytic cell. These two are connected through a voltmeter, and the electrons will be flowing from anode to cathode, and current will be flowing from cathode to anode through the salt bridge. Now, in this case, the reading which you will get here, as I told 1 volt we are getting, you will see this setup in the lab. So this reading we are getting, so this is giving the potential difference between these two half cells. Here the reading which we are getting, this is not indicating electrode potential of any one of the two half cell. This is your, we are getting net cell potential. This is EMF of the cell potential. It is not electrode potential of or oxidation potential of this and reduction potential of this. No. It is here we are getting the potential difference between the two. So here it is here, if you just look here. So what reading? So this we are finding out, or we are measuring cell potential through this galvanic cell. So cell potential is represented by E cell when conditions are not standard. When conditions are standard, it is called standard cell potential. So E0 cell. So E0 cell is a, or E cell if I take up first. So it is your electrode potential cathode minus electrode potential anode. E here I am taking means not standard. Electrode potential of the cell when conditions are not standard, then this is the formula you should remember. And if it is a standard electrode potential, that is cell potential of the cell is at a standard condition, then electrode potential of cathode will also be standard and electrode potential of anode will also be taken standard. Now, so here this is our your E0 when we talk of cathode. So cathode we have got reduction and at anode we have got oxidation. We have got this also. Okay. So or we can also write it as, further we can also write it as E0 Mn plus M minus E0 M over Mn plus. So this is also the method to represent E0 cell. So remember this formula here. Now another important thing just you see, that is practically the electrode potential. So as you have seen, there are two kinds of electrode potential: oxidation electrode potential and reduction electrode potential. But mainly that is your reduction potentials are there whenever it is said standard electrode potential. Standard electrode potential. So meaning of this is they are talking that they are saying it is reduction potential or standard reduction potential. Why? Because here this is more stable. Okay, and that's why that there are many other reasons, but you remember that I will not discuss here further because it will be too elaborated. And so remember that whenever standard electrode potential is talked about, it means they are saying that standard reduction potential. So whenever the when you will see the question, your reasoning question or numericals, then when your values are given, suppose they are mentioning oxidation potential, standard oxidation potential or oxidation potential, you will be converting that oxidation potential into reduction potential. So the, as I told you, here just you see, that is we can know here the cell potential between the two. The cell potential, the reading which we are getting, this is neither of this cell nor of this cell. So if you want to know that what is the electrode potential value of zinc sulfate solution or zinc half cell or oxidation half cell or anodic half cell, then this side potential should be 0. If this is producing no potential, then it means that whatever reading we are getting, that reading will be of this. That will be the electrode potential of this. If you want to know of copper sulfate and then here the reading of copper sulfate, then this side electrode potential should be 0. So if this side is 0, so whatever reading you get, that will be your reduction potential of this cell, reduction potential or the cathode electrode potential. So for that, what is there, when this is taken to be 0, one half cell potential is to be kept 0, then that is called standard reference electrode. So reference standard reference electrode. So that I am going to tell you how this standard reference electrode is made. So this is made how I show you here down. For this, a beaker is taken. In that hydrogen ions are taken. Here I tell you something briefly. When we take hydrogen gas, hydrogen atom, hydrogen electrode, this rod of hydrogen dipped in hydrogen ion, then this half cell will be having electrode potential 0. Electrode potential 0 means here the potential difference will be 0. The rate of gaining electron and the rate of losing electron, that will be exactly the same. So potential difference of this will be potential difference between the electrode and electrolytic solution, that is found to be 0 for hydrogen. So this standard reference electrode is called SHE, standard hydrogen electrode also. So I am going to tell you how this standard hydrogen electrode is constructed. So for that we take hydrogen and for that we take acidulated water. Acidulated water means in water dilute sulfuric acid is dissolved, having concept standard we have to take, so 1 molar solution. So 1 molar solution of this hydrogen ion is taken. So this electrode which we take, like so hydrogen is a gas, so we can't use this rod because hydrogen is a gas. So for that, what is there, that wire is used. Sometimes this wire is of platinum or sometimes it is of copper, and this is having taking some precaution also, is dipped in mercury and all. So that is not required here, that just here that you will take a platinum plate. This platinum plate is coated with black platinum. Platinum plate will be very smooth like the surface of this. So when surface is smooth, this gas which is lighter, it cannot be adsorbed. Adsorb means cannot be taken, not absorb. Absorb means when you put chalk in the ink, the whole chalk will be absorbing. It will be undergoing, it will be penetrating in the chalk, and when I dip my finger into the ink, then it is adsorbed on the surface only. So adsorption, that is surface phenomena, is taking place. So hydrogen gas has to be adsorbed, but if the surface is smooth, it cannot be adsorbed. So it is coated with the particles of the black platinum. So platinum plate is coated with black platinum to make the surface rough, and then I make it little more bigger, then it will be clear to you. So this is platinum mat, this is platinum plate coated with your black platinum, and this is glass jacketed, a glass jacket put up, covered up with a glass jacket which is perforated, having holes at intervals on the side wall, and this is kept in a beaker. Here one side, there is at the base some small piece of unreactive substance is put, and this is to prevent sealing, and here your hydrogen ion aqueous solution, acidulated water is filled, and this is here, this is very long, but I just don't make it that long, and this tube is here, so this is. From here, hydrogen gas is passed at 1 atmosphere pressure. So hydrogen gas is passed, when it comes on this platinum, it is adsorbed there, which is in contact of hydrogen ion. And what phenomena is taking place, that I show you. Two phenomena are possible. One is hydrogen gas that will split up into hydrogen, and it is coming with a pressure on it, so it will split up into hydrogen atom. Then this hydrogen gas, this atom, that will be losing one electron and will be turned into hydrogen ion. This is gas. Sometimes these two reactions are combined and written like this. Half H2 gas is giving hydrogen ion, or like this, half hydrogen ion aqueous and 1 electron. This way, half H2 means 1 atom. So either you write this way or you can write this reaction. So here what do you see? That the electron is being lost. So I take up this reaction. So both ways I have shown to you. Now this reaction will be there one. The second reaction is what? That will also be taking place. That is hydrogen ion aqueous will take 1 electron and will be turned into hydrogen gas. You can take it up like this also, half H2 and half like this. So it's up to you. So both ways I have shown to you. So but I am adding this way. So hydrogen gas is formed. So here your oxidation taking place. This is gain of loss of electron, and here gain of electron, so reduction. So in this type of electrode, when your concentration is 1 molar, temperature is 298 Kelvin, then both these phenomena are taking place at the same rate. So the electrode potential, whether it is your standard electrode potential is oxidation, or your standard electrode potential is reduction. This or this, whatever you take, that is exactly the same and found to be 0, 0 volt. So this side, this is your called sheet and is having electrode potential 0. Since it has both oxidation potential 0, reduction potential 0, so this half cell can be used both as anode as well as your cathode. You can use it in one galvanic cell either at anode, and in the galvanic cell you can use at cathode. So either anode or as cathode, this half cell can be used. Now I will show you its function. Now just see here. Okay. Now you have to find out, suppose the zinc sulfate solution 1 molar electrode potential of this. So this side you will take sheet. How that I make? This is platinum and your glass tube. Here. This is hydrogen gas is passed at 1 atmosphere, and this is perforated. This perforated thing is there, and this is rested on the base, lifted from one side so that it should not be sealed, perforated. That unreacted hydrogen gas should be out. So bubbles of hydrogen will be out, which is not reacting. So here, this side now, electrode potential has become 0. What is this? This is your cathode or reduction potential, and this side, whatever reading will come, that reading will be of this. So in this case, it is found that now what formula I gave you? E0 cell is equal to E0 cathode minus E0 anode.